Hello, and welcome to our video covering topics in section 7.5 of your textbook. In this video, we'll discuss the fundamental theorem of algebra, we'll discuss complex eigenvalues and their corresponding eigenvectors, and then we'll revisit the concepts of trace determinant and its relationship to the eigenvalues of a matrix. Okay, so the fundamental theorem of algebra can be stated in a lot of different ways. One way to state it is as follows. We say any polynomial of degree n with complex coefficients. I say or real here because real numbers are they're complex numbers too, technically, just kind of special ones. But yeah, any polynomial of degree n with complex coefficients has exactly n complex roots if we count them with multiplicity. So let's see what we mean by that. So suppose we have this complex, or we allow this to be a complex polynomial of degree n. Now, normally you would see complex polynomials written with the variable being z, but here I'm writing it as lambda because really the only polynomials we care about right now are the characteristic polynomials of a matrix, and those have the variable lambda, so I'm having lambda here. But okay, this is a complex polynomial, meaning the coefficients are complex, and we're letting the variable also be complex. Then the way your book states the fundamental theorem of algebra says that, okay, if we have some polynomial with complex coefficients, then it splits. And what that means is that's just a shorthand way of saying that the polynomial can be written as a product of linear factors. So to say that it has exactly n complex roots is to say that you can factor it n times, and that is a way to say this very shortly is to say that it splits. And so one thing to note is that these complex roots, they can be repeated, so you can still have, so they don't all have to be distinct. That's the comment about counted with multiplicity. And what's this k doing here? Well, this k is just the leading coefficient here. So yes, this is a different way of saying the fundamental theorem of algebra. You've either got complex roots or you can say it can be factored n times. And again, as I mentioned before, really what we care about is the characteristic polynomial of a matrix. So let's apply the fundamental theorem of algebra to the characteristic polynomial. This tells us we can write the characteristic polynomial as n linear factors, just like this. And if you're worried, wait a second, up here I've got lambda minus lambda 1, and here I've got lambda 1 minus lambda, and I don't have a k here. Well, if you recall from the previous video, the characteristic polynomial has the leading coefficient, the Cn here is negative 1 to the n. And so all I've done is distributed the n negative 1s to each of the linear factors, and that switched the order of lambda and lambda minus 1, or lambda 1. So anyway, this really is the fundamental theorem of algebra applied to the characteristic polynomial of a matrix. And so as a direct consequence of the fundamental theorem, we get that a matrix has n complex eigenvalues if they're counted with their algebraic multiplicity. And this is a complex matrix, but really this could be a real matrix also, has n complex eigenvalues counting algebraic multiplicity. So that's cool. This is something we didn't have before. And let's see this in action. But first, I forgot. I included some bonus content. So yeah, this is completely free of charge, not in your textbook at all. But I think it's cool and relevant, so we're going for it. So here's the bonus content. Turns out that if the coefficients of your polynomial are real, then the complex roots actually have to come in conjugate pairs. This is known as the conjugate root theorem, and it is totally provable with what we know, so we're going to do it. So let's prove this. So we're going to start by assuming that we have some lambda 0, which is a complex root of this complex polynomial, actually of just this polynomial, where, all right, the coefficients are real, but we're allowing the variable to be complex. But the coefficients here are real. So, okay, we've got a complex root of this polynomial with real coefficients. And now our goal is to show that the complex conjugate is also a root. That's what I mean when I say the complex roots come in conjugate pairs, is if you have one complex root, its conjugate is also a root. So, okay, let's prove it. Well, since lambda 0 is a root, this means if we plug lambda 0 into the polynomial, we're going to get that that polynomial is equal to 0, or that expression is equal to 0. And then the trick is to take the complex conjugate of both sides. That's not going to change the fact that we have an equality. And now let's use some rules about the complex conjugate that I made you prove in your pre-assignment for precisely this reason. So one rule is that the sum of the conjugates is the conjugate of the sum, and so you can break up the conjugate over sums. Another rule is that the conjugate of a product is the product of the conjugate, so you can break up the conjugate over products. And then notice that since these coefficients are all real, they're all equal to their conjugates. Like taking the conjugate doesn't do anything to them. And so that's represented here. And then let's one more time use the fact that the product of the conjugate is the conjugate of the product. And we can write, say, lambda 0 to the n. Conjugate of that product is just the product of n lambda 0 conjugates, and so forth. But then what does this tell us? This is just our polynomial, our original polynomial, but now with lambda 0 conjugate plugged in for it. And that, plugging in lambda 0 conjugate, is still 0. So there we go. Lambda 0 is a complex root, then its conjugate also must be a complex root. Cool. And this actually gets us something kind of fun for free. So a fun fact is that if you have a polynomial of degree n and n is odd, and that polynomial has real coefficients, then it has to have at least one real root. Put in the language of characteristic polynomials, you've got a real matrix. If it's n by n and the n is odd, then you have to have at least one real eigenvector. So that's pretty cool. That's like a fun fact you can tell your friends at parties. For those of you who hate having friends. And okay, sure. We actually already knew this. This is just a result, nothing fancy, just the intermediate value theorem. Basically saying if you have a degree n polynomial and n's odd, then all right, in one direction it's going to go off to infinity, in the other direction it's going to go off to negative infinity, and so it's got to cross the x-axis at some point to the intermediate value theorem. But still, I think it's cool, and it's kind of, I don't know, surprising, I guess, to see like complex numbers prove this fact from calculus that about polynomials with real coefficients. I like it. That's why I included it. But okay, let's actually look at complex eigenvalues in action and find corresponding eigenvectors. We're going to look at some examples. And first, we should start with our canonical non-diagonalizable matrix. So we've seen before that rotation by 90 degrees, not diagonalizable, at least not with real eigenvalues and eigenvectors. So, okay, rotation by 90 degrees, that's the matrix 0, negative 1, 1, 0. And if we want to find the characteristic polynomial, all right, determinant of a minus lambda I is going to be this. Characteristic polynomial or equation sets it equal to 0. And before we said, oh, ho-hum, this can't factor. I guess we're stuck. But we're not going to worry about that. We say, oh, lambda squared equals negative 1. I know what that is. That means that lambda is either going to be I or minus I. And so here we go. Here is our complex conjugate pair of eigenvalues, I and minus I. And now let's find their corresponding eigenvectors. And to do this, we just do the exact same process that we did before. We find the kernel of A minus lambda I. So let's do it. So our first eigenvector or eigenvalue is going to be I. And so finding the kernel of A minus whatever, you know what I'm talking about here. All right. Yeah. Plug in I here. We've got this matrix and we're trying to find its kernel. One thing to do, we're trying to get a 1 here. In order to get a 1 here, then we'll multiply. You can see if we multiply the first row by I, then we've got minus I squared, but I squared is negative 1. So in fact, we do get a 1 here, negative minus 1I here. And then we can see right away that, okay, we've got the two rows are exactly the same. You can by inspection tell that any vector that's a multiple of I1 is going to be an eigenvector because it's going to be in the kernel of this matrix. Okay, so we had our eigenvalue I and a corresponding eigenvector I1. And before moving on, I'm just going to note we can also write this eigenvector as the vector 0, 1 plus I times the vector 1, 0. So basically, we can write it as a real vector plus I times a real vector. And this is to mimic the way we often write complex numbers as a real number plus I times a real number. So we're kind of doing this in like vector format. But okay, let's look at what happens when we have our second eigenvalue, minus I. Again, now we are plugging in minus I here, so we get a plus I. Gives us this matrix that we're trying to find the kernel of. Now if we want to make this entry a 1, what we've got to do is multiply it by minus I. And if we do that, then we see that the first row becomes 1I. Again, the two rows are equal, and we can pretty immediately see that the kernel is spanned by the vector minus I1. And now let's also write this vector kind of in the a plus ib format, but now with vectors. And as we see, we've got 0, 1 minus I, 1, 0. And notice, hey, these eigenvectors are complex conjugates. So if we have 0, 1, if we let this be vector v, and 1, 0 be vector w, then this is v plus iw, and this is v minus iw. And it turns out this is not a coincidence. The complex conjugate eigenvalues actually will always correspond to complex conjugate eigenvectors. But I'm getting ahead of myself. We'll prove that in a moment. Let's go back to this problem. What were we trying to do? We were trying to diagonalize this bad boy, something we were not able to do before. So, gosh, I hope we really can do it here. Otherwise, man, this would be a very disappointing slide if we didn't get there. But okay. So, what are our eigenvectors? Our eigenvectors are I1 and minus I1. So let's make them the columns of our change of basis matrix. And then, kind of as though we were dealing with real vectors and real eigenvalues, our diagonal matrix will have the eigenvalues on the diagonal. And then the theory that we've had so far still applies. That tells us that S inverse AS is going to be equal to the diagonal matrix B. So in fact, if we allow our matrix S to have complex entries and we allow our eigenvalues to be complex, then yeah, we can diagonalize A to a diagonal matrix that's just going to have complex values. But hey, that's pretty cool because remember, we love diagonal matrices way more than we don't like dealing with imaginary numbers. I mean, again, you want to find the 100th power or something of matrix, you definitely want it to be diagonal. So there we go. We diagonalized the matrix that we all have lodged in our mind as being the one that we can't. So that's a pretty powerful use of complex eigenvalues right there. And let's move on to another example. This one's going to reveal kind of a deep geometric fact about complex eigenvalues. And so this deep geometric fact is that suppose we have a 2 by 2 matrix and it has complex eigenvalues. So like non-trivially complex eigenvalues, like not real, complex. Then it turns out that matrix has to represent a rotation combined with a scaling. And so this is the deep geometric fact here. You've got a 2 by 2 matrix. Complex eigenvalues mean rotation. So it's not really an accident that the rotation matrix was the one that was not diagonalizable previously, or with just considering real eigenvalues. So okay, let's prove this. So here's our goal. We want to show that if A has eigenvalues A plus IB and A minus IB, so the conjugate pair, where B is not equal to 0, so these are really and truly bona fide complex numbers, then our goal is to show that A is similar to a matrix of the form A minus B, BA. And you might be thinking, what? How is this what we're trying to get? Well, if you recall back from section 2.2, which I agree seems like a lifetime ago, but in that section, the book discusses the fact that any matrix of this form, A minus B, BA, this actually represents rotation through an angle theta and a scaling by a factor of r, where r and theta actually come from A and B. If you have the vector A and B, then r is the length of that vector, and theta is how much that vector is rotated off the x-axis. So, okay. So this is why we want to show that matrix A is similar to a matrix like this, because if we do, then we're saying that, all right, well, in some basis, then we can understand that A is just a rotation and a scaling. So, okay. Let's prove it. Let's get our hypotheses on the table. Suppose we have a 2 by 2 matrix A, and it's got complex eigenvalues A plus and minus IB. Well then, okay, A plus IB has some eigenvector associated with it. It's got to be complex. And so let's call it V plus IW, where, okay, the entries of V and the entries of W are real. So V plus IW is going to be the eigenvector associated with eigenvalue A plus IB. Our first step is to show that the eigenvector associated with A minus IB has to be of this form. It has to be the complex conjugate of V plus IW. So, okay, so that's our first step. Show that this is actually an eigenvector associated with the eigenvalue A minus IB. First thing we're going to do is we're going to consider A of this eigenvector and its complex conjugate, and we're going to do that two ways. So in the first way we calculate the complex conjugate, we're going to use the fact that product of conjugates is the conjugate of the product, conjugate of a product is the product of the conjugates. And so we're going to split this up over these two, or break it up over the matrix and this vector. And you might be wondering, wait, what does it mean to take the complex conjugate of a matrix? And that just means, like, we're going to define that to be taking the complex conjugate of each of the entries. And you can confirm for yourself at another time, or right now and posit that this rule still works, even when we're dealing with matrices. But okay, so we've got this. And then if the entries of A are all real, which this is where we are starting from, we're assuming A has real entries, then okay, the complex conjugate of A is just going to be itself. And then the complex conjugate of V plus IW is just going to be V minus IW. Okay, so that was one way to look at the complex conjugate of A V plus IW. Now let's look at it another way. Well, remember, V plus IW was an eigenvector. And so A V plus IW is going to be A plus IB times V plus IW. And now, all right, we're taking the complex conjugate of all of this. Again, break it up over a product. And so this is equal to A minus IB times V minus IW. And now, remember, we started at the same place, just the complex conjugate of this. And so what these calculations tell us is that A times V minus IW has to be equal to A minus IB times V minus IW. And all this is saying is that V minus IW is an eigenvector with the eigenvalue A minus IB. So there we go. We've shown what we wanted. Starting with A plus IB, assuming it has some complex eigenvector, we've shown that the complex eigenvector V minus IW, the complex conjugate, is also an eigenvector with eigenvalue of the complex conjugate. Okay, that was a mouthful, but we're there. We got it. So step 1 proved. Now I'm going to need some room. So yeah, step 1 is still here, but I'm removing the kind of justification for it, but we've proved this. So now what's step 2? Step 2 is to show we've got this matrix S such that S inverse AS is in fact of the form we want. So this is what's going to take us home. Is we're going to show that matrix A is similar to this rotation scaling matrix. One thing that might be a little surprising is that, so S here, this W and V come from the eigenvectors, V plus IW, V minus IW. It's the same W and V, but now their order is switched. So this W is here and the V goes second. But notice, so that's one kind of thing that you might not have expected. Another thing you might not have expected is that these are real, right? So S is a real matrix. So we are doing everything here is totally kosher, legit. We are using complex eigenvectors to come up with a real matrix equation. So that's kind of surprising. But all right, so let's do it. Let's show that this is true. So first, let's do some calculations. So since V plus IW is an eigenvector, A times V plus IW is just A plus IB times V plus IW. And then distributing, like foiling out, let's see, we've got AV, and then IB times IW is going to be I squared BW, so minus BW. And then we've got plus IBV, and then plus IAW. So, and factoring out the I, we get this. Just simple complex algebra. Simple complex algebra. That was fun to say. Okay, let's call this equation 1. Now let's do another calculation. Basically the same calculation, but now with the complex eigenvector V minus IW. This has complex eigenvalue A minus IB, and if you do the same calculations as above and group like terms, you'll see that you get the same thing, except instead of plus I BV plus AW, you get minus I BV plus AW. But otherwise, they're the same. And we'll call this equation 2. And now, what we're going to do is we're going to add these two equations together. So first, let's just look at what's happening on the left-hand side of this equation. So this is taking A times V plus IW and adding it to A V minus IW. And then using linearity of A, this is AV plus IAW plus AV minus IAW. All right, these IAWs cancel, these add together. So the left-hand side, if we add the left-hand sides of these equations, we get 2 times AV. And what's going on if we add the right-hand sides? Well, remember, the only difference here is that instead of a positive, that's plus I here, we've got a minus I. And so when we take these two right-hand sides and add them together, these guys are going to cancel. These are going to add together. And so the right-hand side equals 2AV minus 2BW. And so setting these equal and canceling 2's, we get this equation that A times V equals, little a times V minus little b times W. All right, we're going to go through a similar process, but now we're going to subtract equation 2 from equation 1. So again, what's happening on the left-hand side? Well, okay, AVW plus IW, or AV plus IW minus AV minus IW. Use the linearity of A. I'm not going to go through all the calculations, but you can check yourself that this is going to be equal to 2, that the AVs are going to cancel, and we're going to get 2I AW. On the right-hand side, okay, now we are subtracting the left-hand side, or we're subtracting this off, and so these AVs are going to cancel, these BWs are going to cancel, and now we're going to get 2I times BV plus 2I times AW. All right, and these two things have to be equal, so let's cancel the 2 i's from everywhere. And putting those together, we get this equation. AW is B times V plus A times W. And so now, with these equations in hand, let's consider a basis where the first element is W and the second element is V. And if we do that, what do these equations tell us? Well, okay, our first element is W. A times W is little a W and little b plus little bv. And so the first column is going to be A, B, because remember, W ends up being the first the first vector here. So the first column is going to be AB. And then the second column is going to be, well, what does A do to V? A takes V to little av minus little bw. But remember, when we're writing it in the coordinates wv, this is going to mean the second column is minus ba. So yeah, we get this matrix, A, B minus BA. And look, this was the matrix we wanted. And so if we let S be the columns of this basis, W and V, then in fact, yeah, we get that S inverse AS equals B, just like we wanted. So there we go. Hopefully you are convinced that complex eigenvalues mean rotation and scaling. And the scaling is because A and B, the vector AB might not be a unit vector. Okay. Let's do one more example. So let's consider this 3x3 matrix. And what is this matrix doing? Like, what is the transformation doing? Well, if you think of each column as being where the standard basis vectors are taken, then geometrically speaking, this is going to take the x-axis to the y-axis. This column means that we're taking the y-axis to the z-axis, and this third column means we're taking the z-axis to the x-axis. So geometrically, that's what's happening. And let's use complex eigenvalues to see if we can understand this transformation a little better. Okay, the characteristic polynomial, taking this determinant, you get, put minus lambdas all on here. I don't know. I use Laplace expansion, but you get this as the characteristic polynomial. And this can factor. You might not have seen it right away, but I'll pull out the factor of 1 minus lambda. And so this is our characteristic equation. And again, before, you would use the quadratic formula on this and say, oh, I don't get real numbers under the discriminant, in the discriminant it's negative, so I guess I'm stuck. Not this time. Let's plow ahead. So this factor here definitely gets us a lambda equals 1. Our first, eigenvalue is lambda 1. That's going to be 1. And then here, use the quadratic formula, and we get, all right, lambda 2 is going to be minus 1/2 plus I root 3 over 2. And then our third eigenvalue is going to be the complex conjugate of that. Okay, so we've got 3 eigenvalues. So let's find 3 eigenvectors. Well, for lambda 1 is 1. find the eigenvectors. We got to find the kernel of this matrix. And if you do that, you can, you can check that this actually is in the kernel. But yeah, you could also, like, if you'd gone through the process of finding the kernel, you would find, okay, yeah, we get this eigenvector 1, 1, 1. Similarly, though considerably more painful, if you have the eigenvector, the eigenvalue lambda 2, then all right, you want to find the kernel of a minus lambda I. So you've got, it's kind of like it just looks like a headache. And you are welcome for not making you do this yourself. But it turns out if you did the calculations, this would give you the eigenvector 2 minus 1 minus I root 3 minus 1 plus I root 3. And then we're going to write this in the A or V plus IW form like this. And then because of what we showed already, we don't have to calculate the third eigenvector because we know that the third eigenvector is just going to be the complex conjugate of this eigenvalue. So, okay. Let's now make our basis the first eigenvector, 1, 1, 1, and then similar to how we did it just in the previous slide, where we were trying to show that our 2 by 2 matrix with complex eigenvalues had an essential rotation component, we're going to do something similar. So now for our second two vectors, let's have them be the W and the V here. Okay, and if we do that, what does our matrix B look like? Or equivalently, writing A in this basis, what does it look like? Well, okay, we've got 1 and zeros on the first column, zeros on the first row, and then, all this business. And if you stare at this long enough, you will see that this business here is, if we were considering just a 2 by 2 matrix, this is 120 degree rotation. Cool. Now, you can go back and check, and should, that in fact these two basis vectors here are perpendicular to 1, 1, 1. And so these two basis vectors here are in the plane perpendicular to this. And so really, this transformation represents a 120 degree rotation where the axis of rotation is the line spanned by 1, 1, 1. And if you think about it, like, let's go back and think about our original geometric interpretation. This makes sense. If you think, okay, well, if you had to rotate to get the x-axis to the y-axis, the y to the z, and the z to the x, then it makes sense that you can't see like the hand gestures I'm making right now, but yeah, you've got a line going through 1, 1, 1, and you're just, rotating by 120 degrees. Well, I see it at least. Hopefully you do too. Yeah. So all of this success, we didn't actually, I guess on the previous slide, diagonalize that matrix, but we could have, right? We could have found, we could have diagonalized it. We got 3 eigenvectors. So yeah, this might make us wonder, like, oh, does allowing complex eigenvalues let us diagonalize everything? And sadly, no. And in fact, this is proved with our old friend, the matrix 0, 0, -1, 4, 4. So this is something that we saw in our last video, and I think I gave you a pre-assignment problem on it. But as we saw in the previous video, the characteristic equation for this matrix is going to be lambda minus 2 squared equals 0. And so we get one real eigenvalue, lambda equals 2. And notice, this has a one-dimensional eigenspace. The span is 2, 1, and we calculated this previously. But then here's the thing I wanted you to notice before, because I'd forgotten about that part. But notice that complex eigenvalues can't save us here. Like, this characteristic equation was factorable. We had n factors, or in this case, 2. So the problem wasn't that we had n factors, or that we didn't have enough factors. The problem was that the dimension of our eigenspace wasn't enough. And so this matrix is really and truly not diagonalizable. And it's not, and you could run into similar issues if you had complex roots, but you had a multiplicity issue where the algebraic multiplicity was greater than the geometric multiplicity in some sense. So no, not everything is diagonalizable. But what about the next best thing? I mean, diagonal matrices are amazing, but triangular matrices are pretty sweet as well. I mean, definitely taking their determinants is no big deal. So is it triangularizable? Well, to discover the answer to this and other exciting linear algebra questions, take an advanced linear algebra course. We won't talk about it here, but this is a question. A lot of ink has been spilled on this. And you might have the pleasure of seeing it one day, but not today. Okay, let's really quickly revisit the relationship between the trace, the determinant, and the eigenvalues of a matrix. So this is theorem 7.5.5 in your book, and it says, suppose you have an n by n matrix A, and it's got complex eigenvalues lambda 1 through lambda n. This is with multiplicity. Then it turns out that the trace of A is the sum of the eigenvalues, and the determinant of A is the product of the eigenvalues. And so I want to say a few things here. One, this is just like theorem 7.2.8, but in that theorem, we had to assume that A had n eigenvalues. And now we don't have to do that because the fundamental theorem of algebra guarantees that we have n eigenvalues with multiplicity. So that's one thing. This is basically the same theorem, but now, we don't have that assumption because we're allowing complex eigenvalues. But you might be worried. Wait a second. Well, if the trace is the sum of a bunch of complex numbers, how do I know it's real? And similarly, if the determinant is a product of a bunch of complex numbers, how do I know it's real? Because if A is a real matrix, its trace and determinant have to be real. Well, these are real due to the conjugate root theorem. Because remember, if A is real, then if any of these are complex, then their conjugate has to show up as well. The sum of a complex number and its conjugate is real, and the product of a complex number and its conjugate is real. And I think I had you prove both of those on a pre-assignment. So I'm glad I did that. And then last thing I want to say is that the arguments for why this theorem is true are exactly the same as the arguments for why theorem 7.2.8 is true. And with that, I think we're done for the day. See you in the next video.